Okay, I think we're ready to start. So welcome to our new webinar hosted by the Norwegian National Competence Center for High Performance Computing. As many of you know, Competence Center is a partnership between NRIS, SINTEF and Sigma 2. And one of the most important contributions Sigma 2 bring to the partnership is the competence between NRIS, which is a Norwegian Research Infrastructure Service, a meta-organization with Sigma 2, University of Tromsø, NTNU, University of Bergen, and University of Oslo, where today's speaker comes from. So Jørgen Nordmoen is a senior engineer at the UCIT, the IT group at University of Oslo, and a team lead for the NRIS GPU team. His main focus is on helping researchers get started with and optimizing the use of GPUs on the Sigma 2 HPC infrastructure. His background covers a broad spectrum of machine learning, ranging from swarm intelligence to deep reinforced learning. He has a PhD in evolutionary robotics from the University of Oslo, and has published both on software simulation and real-world robotics experiments. In this webinar, you get to know more about machine learning and how this is becoming one of the biggest applications in high-performance computing. For many use cases, access to computing resources of a single computer is no longer sufficient, and scaling out is the only option. Couple this with a growing size of data that must be fed to the algorithms during training. It's no wonder that many researchers are turning to HPC for their computing needs. So that so now that we are starting the webinar, you are, as an audience, obviously free to ask questions through the Q&A functions of Zoom, and I will try to answer those questions during the session. So I'll leave the floor to you now, Jørgen.
Thank you so much, Roger. I hope everyone's doing well this morning. So today I thought we would discuss a little bit about distributed machine learning in an HPC context. And hopefully by the end of this webinar, you'll understand what I mean with this title. So the agenda for today, we'll start with a very quick introduction. I'm assuming most of the people in this webinar are slightly familiar with machine learning, so we won't go too much into what machine learning actually is from a basics, but we'll just get a shared understanding so that you know what I mean when I say machine learning. The second part of the introduction is the HPC context, and this is the part that we don't expect you to know that much about and hopefully are more interested to learn. And by the end of the introduction, I hope you understand more what I mean with an HPC context. Then the main meat of this presentation is how to distribute your machine learning workload over multiple machines in a cluster. And we'll see what's needed to adapt your code, how it works, and we'll try to give you a few pointers on data handling, as that is a really important topic when distributing. And lastly, I'll spend a couple of minutes just telling you what we can give you apart from webinars such as this within NRIS and Sigma 2. And we'll talk a little bit about upcoming systems, which I think is really interesting in this context, especially when it comes to distributed machine learning. So what do I mean when I say machine learning? Well, today we'll focus on neural networks. And of course, there are a lot of different types of neural networks, and we'll cover this talk covers a broad range of these neural networks and are applicable to multiple. So if you are a researcher in natural language processing, you're probably most familiar with transformer networks. If you're doing image research, then recurrent neural network or LSTM networks might be your flavor, or just deep neural networks in general. And we'll focus on that. In addition to that, another important part here is that we sort of assume that you have a lot of data to shoot through. If you're doing research, more one-shot research learning, or maybe you're more interested in reinforcement learning, then the techniques talked about in this webinar might not be perfectly suited for your use case, especially for reinforcement learning, where you're spending more time simulating most likely on the CPU. It's not as relevant for this framework, so to speak. But it's important to note that what we will talk about could be used for reinforcement learning as well. But we sort of assume large neural networks, a lot of data, and a good speed up on GPUs. So that's the machine learning context. But what do I mean when I say HPC context? Well, HPC, computers, clouds, laptops, all a lot of technical terms that needs some explanation. So high performance computing is basically the same as cloud computing, but not exactly the same. So what we've seen in the later years is that hardware is becoming commoditized. So it's cheaper for the supercomputer centers to just buy off-the-shelf units and connect them in different ways. But in principle, it's the same hardware as cloud computing. So you could get the same CPU in a cloud computer setup, but the main difference between cloud computing and supercomputing is the usage philosophy. And what that means is that in a supercomputer context, we usually have a queuing system. There are shared resources and exclusive access. So we won't go into too much detail here, but suffice it to say, when you rent cloud computing resources, you pay for the whole time that you're there. But in a supercomputer context, you sort of define batch jobs that you submit, and you have to specify a little bit about these jobs. And then you only pay for the time that you actually use. And you get exclusive access to the resources that you request in the HPC context. So let's go into a bit more details here. And I have tried to make a few illustrations. And what you're looking at here is at least how all of the supercomputer resources in Norway function. And on the left side, you can see you as the user come in, accessing the system through what we call login nodes. And these login nodes are just basically machines that ensure that you don't have access to all the expensive hardware right out of the gate. So you have to log in to these login nodes, hence the name. And from there, you can run jobs that the login node sends to all of the machines in the system. So what I've tried to illustrate here is that we can have what we call partitions, and that's that can be different machines with different special purposes. And I'll come back to concrete example, but you can think of these partitions as different machines that have different tasks. So partition A might be optimized for AI, partition B might be optimized for simulation, and partition C might be optimized for large memory requirements. And some of the underlying assumptions in HPC is that you have this shared storage. So I haven't drawn the lines, but you could imagine lines from shared storage out to all of these partitions. So all the partitions and the login node can access the same shared storage. And these are usually huge file systems with surprisingly good performance, all connected through really powerful interconnects. And that's another difference between cloud computing and HPC. So usually in cloud computing, you have high capacity or high bandwidth networks, but they're usually optimized for throughput, not latency. While in HPC, we usually have interconnects that allow for huge throughput, but are optimized for really low latency. So it should be cheap for one machine. So for instance, if you have two machines in partition A, these should be able to talk to each other really quickly. And so from the login node, we run what we in the supercomputing business call jobs. And so these jobs are just a specification of what resources do you need, for how long do you need them, and what should they actually do. So here I've tried to illustrate what a job might look like. So what I've tried to illustrate here is that we have a job. It requires 2 machines or nodes in HPC parlance. And each of these 2 machines have possibly 2 attached GPUs that the jobs want to utilize. And you can also see I've tried to illustrate the global shared file system, which both of these machines can access. And so they can share resources over this interconnect. They can access the same file system. They see the same thing. So what's good about this sort of, and the reason that we do it is that it allows exclusive access to these resources. So in our systems, we can say that when you get, if you ask for a whole machine in one of our clusters, no other operations will be going on there. Basically, and you have access to this global file system, which I've mentioned a couple of times, that gives you the same view all the time, and you have a really fast interconnect between the machines. However, the downside of this is you have a limited time, so you can't just open up a Jupyter notebook on one of these cluster nodes and have that running in the background, do stuff for you. You have to go a little lower level than that. We can't dynamically scale resources, at least not easily. So once your job has started and been allocated resources, that's the resources for the end of that job. So you can't, in the middle of the job, sort of detect that you need more resources and then go ask for more resources. And this sort of all leads to what I've phrased as offline development. So you can't really work in the same context as you can in cloud computing, where you can start up a Docker image and then find out that I need more resources and then spawn multiple Docker resources. You have to let your job run to completion and then change the requirements, then start again, and so on and so forth. So it's a bit of a different philosophy, as I've written in the previous slide. And here is a concrete example of what I mean. So Betsy is the most powerful supercomputer in Norway. When it came online, it was the 56th quickest supercomputer in the world, I think. Probably fallen a bit since then. But here you can see I've listed up the different partitions from the previous slide. So we call them A, B, and C, but here they actually have names that corresponds to basically what their intended use case is. So we have a partition normal, which consists of almost all of the computing power of Betsy that are 1,340 nodes, as you can see, with CPU, memory, and all the other stuff. We also have an accelerated partition, or Excel partition, which consists of GPUs. And we have this pre-process partition, which allows users to work on their data before they send it to one of the 2 other partitions. And as you can see, there is quite a good interconnect here for Betsy. So that's the HPC context. But how do you then combine HPC and machine learning? And if you're familiar with machine learning, you probably recognize the logos on the left here, PyTorch and TensorFlow. If you're familiar with HPC, you'll be familiar with the logo in the middle, OpenMPI. And when you combine those 2 together, you get what you have on the right side, and that is the framework Horovod. So MPI is a communication library which has been used in HPC since basically before I was born. And it's not that much use outside of HPC because it's intended for low latency application and not really cloud environments. But that's why frameworks such as Horovod are so important, because they can sort of abstract that away. So how does all of this come together and work so that you can take your machine learning training that you're running, hopefully on a powerful workstation with one or multiple GPUs, and then come to our systems and distribute that out to multiple systems, because that's what you probably are interested in learning from this webinar. So, as I said and summarized here, Horovod combines machine learning with MPI. Horovod supports multiple machine learning frameworks. So it's not just PyTorch and TensorFlow, although those are the main ones. Horovod supports both inter and intra-node distribution. So if you just want to dip your toes in and test this on a single machine with multiple GPUs, you can use Horovod for that, and then later distribute to multiple nodes. Since this is a machine learning framework and first and foremost designed for high performant machine learning, you can assume that it's using GPU primitives for inter-node communication. So that's basically NCCL and RCCL, if you're familiar with those terms. But what that basically means is that Horovod will use the most optimized primitives for doing communication internally on a machine. And when we come to the future machines, you'll see also that Horovod will also scale differently from machine to machine as well. The nice thing about Horovod, if you're using PyTorch or TensorFlow already, is that there's very little adaptation. Since this is a Python framework, a lot of work has gone into making Horovod integrate well with these other frameworks and allowing for getting started really quickly and getting good performance really quickly as well. And the last point is probably the most important for this webinar. Since Horovod uses MPI under the hood, we can sort of think of Horovod as HPC native, at least for us in the that works with supercomputer daily. Horovod is much more HPC software than a lot of other machine learning frameworks. So let's go and see how easy this is. And I've used the simplest example, the NIST character recognition. So let's hopefully see. Okay. Hopefully now you can.
I ask a question regarding Horovod and MPI. So would it only work in HPC context, or would it also work for example, two workstations connected together on Ethernet?
That's an excellent question, and it will actually work with these connected together. You'll just have to ensure that MPI communication work between these two nodes. If you're just using Ethernet, there might be other simpler ways to do this, because MPI can be a bit fiddly to set up. And the reason that we're focusing on MPI today is that I can say probably with 100% confidence that all supercomputer centers in the world have some form of MPI installed. So that's why we're focusing on that. As I mentioned, on a single workstation, it's probably a bit easier, because then there's really no setup of MPI. It will just work. Over two computers, it should be doable. It shouldn't be that hard, but you might need a bit of fiddling to get it to work. But an excellent question, and it should be possible, yes.
Okay, thank you.
Yes, so what we're seeing here is the tutorial that sort of follows this webinar, which we will publish quite soon. But what we're looking at here is basically TensorFlow training on the MNIST training dataset to recognize characters. And I just want to show you here how easy it is to integrate with Horovod. And for those of you that are familiar with PyTorch or TensorFlow, hopefully you'll see you'll be familiar with most of the terms, apart from the small Horovod stuff that we need. And initially here, what we see is that we need to initialize Horovod, and that sort of allows Horovod to instantiate the MPI communication. And if you have ever programmed with MPI, you'll be familiar with this initialization call. The next thing is that we have added just a debug printing so that you can see how many ranks in MPI, or how many tasks is probably a good way to explain this, have started up. And this if here ensures that only a single one of these tasks that MPI has started actually output this. So again, coming from MPI, this should be really familiar. Coming from other frameworks, not having worked too much with MPI, this looks really strange. But what MPI does is that it starts the same program on all of the different machines that we want. So again, let's say we have 2 machines and we want to run a task on each of them. MPI will simply just launch the same program twice, once on each machine. And MPI will then give what's called a rank to each of them. And a rank is basically just a number. It tells you which ID your MPI process has. And then to avoid having all of the MPI processes printed the same thing, we can then guard this statement with a special, with just checking the rank. And rank 0 is usually what we call the root rank in MPI. But we could have used any number here, but you're guaranteed to always have, you're always guaranteed to have the 0th rank, because as long as MPI starts just a single process, that will have rank 0. But in theory, if we knew, for instance, that we knew there will always be at least 10 ranks, we could have also said 10 here. So, okay, we've initialized MPI. Going a bit further, we see just some GPU initialization. We'll quickly jump over that. Here you can see that we load data. This looks very much like TensorFlow Keras loading, and that's because it is. There's no special magic here. The first Horovod speciality actually comes here. You see that we use a special function in TensorFlow called shard on the dataset, and that basically tells TensorFlow that we want to only use a small partition of the full training dataset on each of them. And here you can say that you can see that we have num shards fits very well with Horovod size, so the number of ranks in total, and the index, or the slice that we want to use in this current rank, corresponds to our rank. And what this does is that we easily share data between all of the ranks, because we don't want all of the ranks to train on the same data, because then we would just get, we would expect to see the same weights in our neural network, and we don't get any speed up from using that. So by sharding our data set, we ensure that all the ranks see different data. When they then train later on, we'll see that they'll hopefully update with different weights that we then combine together. So again, we create our model. There is nothing special here either, just basic TensorFlow Keras modeling. We define a learning rate, and then we scale that learning rate with the size of our MPI setup, so the number of ranks that we run, and that's to reduce training per neural network. we then create our optimizer, in this case, an Adam optimizer. And then again, we do some Horovod special magic, and that's to create a distributed optimizer. So we need to tell Horovod, first and foremost, which optimizer we want to use on each learner. But we also need to tell the system as a whole that we need to distribute this to get together, as we'll see later how that's done. Again, we compile our model, nothing special there, ensure some checkpointing. And then we also have more speciality for Horovod. So we need a couple of callbacks here. And the first one is we need to broadcast the network initially when we start. So this 0 here is actually which rank should distribute that. And this is to ensure that all of the neural networks start with this from the same state. So if we load the network from a previous state, we need to load that into all of the ranks, and we do that from rank 0. And if we create a new initial random neural network, we also need that to be equal among all the ranks so that you don't get divergent too quickly. Again, since we now have n number of processes that are all performing learning, we need to average the data coming back from that. That's more to do with TensorFlow and how that collects data, but it's needed as well. So it's nice to learn. And lastly, we don't strictly need this, but we add a warm up so that the learning rate sort of transitions slowly from what we wanted to start with, or a slightly higher learning rate, to our conservative learning rate over some times, so that we don't get these vanishing gradients straight away. Once this is done, we want to do model checkpointing, right? We want to save our neural networks, but we only want to do that for one rank, because if all of the ranks try to save to the same file, since this is a global file system, they would all be seeing the same thing and trying to write and potentially overwrite each other. And that's why we ensure that only one rank actually saves the model. And we then just go ahead and train as we would usually do. And we also, for this tutorial, we want to output some training or some information during training. And we can then again use Horovod rank equals 0 to see if we should output verbose or not. And that's to ensure, again, that just one of these processes outputs information. And what's nice here is that we can scale the number of steps per epoch per the total number of ranks that we're running. So if we're running on 2 machines, we can have half the number of epochs, because the number of training steps would then still be the same. So if we required 500 training steps on a single machine with just 1 GPU, if we then scale this up to 2 GPUs on 2 different machines, we could then halve the number of epochs and still get the same number of training steps. And again, then last thing we do here is just to check the model. And we do that again just for rank 0, but that's actually not strictly needed to show Horovod. So hopefully that's given you a good indication of how little is needed to add Horovod to your code. Again, if you want to look more into details for this, we'll publish this tutorial as soon as possible so that you can follow it at your own pace, because we have to go quite quickly today based on time, unfortunately. But what I want you to be left with here is just how little we had to specialize the code. And if you think about what Horovod is doing behind the scenes here, that's actually quite remarkable. This training here can be scaled from one machine to probably several hundred, maybe even thousands of machines if you have enough data. A lot of caveats, of course, but just think about that, being able to do this little adaptation and get so much out of it. That's quite remarkable, I think. So let's try to summarize what Horovod actually does. And again, I'm using a couple of terms here that I've tried to stay true to, but what I'm trying to illustrate here with MPI rank, that's one instance of our program running. And node 1 and node 2 are two different machines. They're, of course, connected through our interconnect, our high performance interconnect, but they're not on the same machines. While the two MPI ranks on node 1 or within the node 1 box are on the same machine and can then communicate quicker. On the left here, we see we have a neural network that we want to train, and we have some training data that I've sort of already pre-sharded into these three boxes that we also saw that we did with TensorFlow. So the first thing that Horovod does is that it distributes the neural network, or it replicates the neural network on each of these machines. So as you can see, I've tried to sort of indicate here that the neural network is now connected to each GPU, and each MPI rank has gotten one part of the training data. And it's important to note that this is not the same data. It's part of the total training data set, but it's unique for each MPI rank here. What then happens is that we do a training batch. And what I've tried to illustrate here is that the neural network sort of updates its weights, but it updates them in a different way for each of these neural networks because they see different data, right? After the training batch is over, we have three neural networks that have slightly diverged from each other, hopefully not too much because they should be learning the same things. We then perform communication between these MPI ranks. So you can see here, I've tried to illustrate that we do communication all to all. We're actually doing an all reduce is what it's called. And the thickness of these dotted lines sort of indicates the speed of which we can communicate. So going from the GPU on node 2 to the GPU on node 1, we can see that, okay, here we have to go over the global interconnect, which in most cases is slower than going directly from GPU to GPU on the same nodes. But hopefully it's quick enough and we can scale it in such a way that we still get something out of this. So hopefully doing training with these three MPI ranks should be quicker than having just two MPI ranks on the same node. But that's something that you always have to test for yourself to check if that's the case for you. After we've done this all reduce, what actually happens is that the neural networks are, the weights are distributed to all of our ranks, and then all of the ranks do a reduction on these weights to get one new network. And since all the data is the same and the operations that we're doing are the same, we end up with new networks that should be sort of the average of these three processes. So you can see now we are in the same step. So going quickly back a bit, we did a training batch. We got different weights. We did some communication to share the neural networks, the weights between all of our ranks. And we ended up with the same thing again. And now we're ready to do a new training batch and let the neural networks train again. Hopefully that made some sort of sense. And that's, in a very short amount of time, basically how Horovod works. And I hope if you find this interesting, you'll read more about that later on other pages that can explain it better than I can. I also mentioned in the introduction that we wanted to give you a few pointers on data handling, and the reason for that is that data handling is really important, and even more so in a distributed context. We have this global file system, but the challenge there, of course, is that that global file system can't be as quick as a local quick SSD. We can do a bit on our system to hide the latencies, but still it's slower than just having the data already on your machines. So that's why it's important to shard the data in TensorFlow terminology, or create a distributed sampler in PyTorch terminology. And you need to do this as early as possible. Actually, you want to do this before you start reading. And the reason for that is that you want each of these MPI ranks to only read the data that they need from the global file system. So the global file system is really good at letting each of the machines read from the same data set, but at different points in the data. And so if you shard your data set even before you start reading it in, you'll get a lot of speed up, because the machines only need to load the data that they're actually going to use. And by doing this, you give each of the MPI ranks different sets of data to work on, and ensuring that you actually have different neural networks, because that's a challenge that many people encounter when they first start to use Horovod, is that they implement it, they start Horovod exactly as the Horovod tutorials explain that you use it, and then you don't actually see any speed up. Your network comes out correct, but you've used twice as much resources and didn't get any speed up. And the reason for that could be that you didn't share the data set. So each of these MPI ranks on your resources just read in the same data, just did exactly the same thing. They trained the same neural networks. So you just got 2 instances of the same neural network. When you then do the all reduce, of course, you get the same neural network out, and you don't actually see any speed up. You don't see difference from training with Horovod than just training on a single GPU. So it's important to think about data handling when you start this. And our tutorial goes into that further. Another important part is that a lot of supercompute clusters also offer a local file system in addition to the global file system on each of the compute nodes, where you can actually preload a bit of your data. So what I've illustrated here is how you can do it with TensorFlow. So if you call cache on your dataset, what TensorFlow will then do is load the data and save it to this local scratch, as we call it in an HPC context. And if that's a fast flash disk, then when you're if you're reading more data than there is memory on the node, you will just spill that into the fast flash and read it from the fast flash instead of going to the slower global file system. That's also something to keep in mind when you scale upwards. Again, remember, initially I said this is for the users with a lot of data, and especially caching. I've also added a small caveat to this slide, and that is, as you saw when we introduced Betsy, our supercomputing nodes have quite a lot of memory. And so if you then have a dataset that's smaller than 500 gigabytes, you don't actually need the cache, because TensorFlow will never spill anything to disk. So different sets of trade-offs and things to think about. But distributing and going to a cluster setting is, of course, different than just working on your regular workstation. But hopefully by going this route, you get access to more resources than what you would otherwise have. So that's a whirlwind introduction to Horovod and distributed learning. So what I wanted to just spend a couple of minutes on now is just to tell you a little bit what we can offer you. So what NRIS can offer you in terms of GPU, AI, distributed learning, and all of that. So first and foremost, as Roger introduced, what NRIS and Sigma 2 bring to the table is disciplinary experts. So experts in biochemistry, physics, statistics, of course, HPC optimization, that's our bread and butter. And also now lately GPUs is what we've started offering. So I think last year we started offering that. And we can offer you extended support, so we can join forces with you to help you optimize your system. And that's especially interesting for this next slide, in that we have a lot of GPU resources, and you can contact us if you need more. But we also have access to future HPC system. Of course, that's not really true. We don't have access to the future yet, but coming this year is this Lumi supercomputer. And there's a supercomputer being set up in Finland. And as you can see from the spec sheet here, it's a monster of a computing system. And Sigma 2 is a member of the Lumi consortium, and that gives Sigma 2 access to a set amount of resources that we can give out to Norwegian researchers, and we can also help you get started here. So if you have large requirements for machine learning, please contact us, and we can help you find the correct fit for you, if that's Saga or Betsy, or if that's a transition to this new Lumi system. That's what we're here for, to help you get into that. And I also teased this a bit in the start, so I should probably say it here. A really interesting part of Lumi is that, as the slides say, it's only comprised of GPUs. So all of the compute power comes from GPUs. It's slated to be the third fastest supercomputer in the world and the fastest in Europe. But what I find most interesting here is that the GPUs are actually directly connected to the global interconnect. And what that means is that each of the GPUs on node A can talk directly with the GPUs on node B. And what that means again is that if a GPU on node A wants to send data or fetch data from node B in a traditional supercomputer setup like Saga or Betsy, unfortunately, the GPU has to communicate with the CPU. The CPU has to go to the network card. The network card sends it over the interconnect to the other machine. The network card on machine B accepts the data, sends it to the CPU, sends it to the GPU. And then that's how we share data on Saga and Betsy today. But on Lumi, the GPUs can directly just send data straight over the interconnect. So you don't even need to talk to the CPU to share data. And that's a characteristic that will be really interesting to see from Lumi.
So we do have a question, Jørgen. So one of our audience have asked whether or how IO intensive the process of the communication between the learning tasks are, and how much faster would fast acceleration be versus increasing the speed of the CPU or GPU?
Yeah, so that's a really good question. And the answer to that, it's of course, it depends. But the larger your network is, the more data, of course, you need to transmit, because we need to do this all reduce operation that I've mentioned briefly. We need to sort of send data from all the GPUs to all the other GPUs, and then collate that into a single network again. And the larger your network is, the larger the communication here becomes. And this is also why you see this distributed network using MPI, because this is not a lot of data, and that's why Horovod isn't really used in data centers, because the main bottleneck when doing distributed training is latency. So how fast can I send my weights from one GPU to the other GPUs? And if you're on only one node, that's of course really fast, because both NVIDIA and AMD and Intel have their own intra connect between the GPUs. So that's really fast, and we use an NCCL, for instance, to do that. But when you then go from one machine to the other machine, you need this fast interconnect that supercomputer offers. So yeah, I hope that was the answer to that. There isn't a lot of data, but it needs to move quickly, or else your GPU most likely trains really quickly, then has to wait for network communication, and then trains quickly again. And the reason that we want to do this is because we can share our data, as I talked about before, to a lot of machines. So if you have terabytes of data that you need to train on, it's quicker to send that to maybe 10 machines, say. So each of these 10 machines have 100 gigabytes to train on, and then share between them instead of trying to just do that on a single machine. So distribution, and that's something of course I should have mentioned, is when you have really a lot of data.
Okay, thank you. I don't see any other questions, so I guess it's time to end the webinar. So the webinar was recorded and will be published on YouTube in a channel, and you can find the link on the same web page where you signed up for the webinar. You can also find contact information there if you want to contact us with questions, and we can basically answer anything related to these topics. And we'll also share the presentation Jørgen just presented. And I guess you also have your contact information in the presentation.
Yep.
And we'll also publish the tutorial shortly. So I'm looking forward to that and trying it myself. So I think it was a really good webinar, really interesting topic. So thank you for that.
Yeah, thank you all for attending the webinar.
Okay. Thank you all, and have a nice day. Bye.